Hello everyone, you're welcome to another class. It's another time to have a deep dive into the topic electromagnetic field, and I hope that you pay rapt attention and you learn a lot on this one. So I'll be taking you over to my screen right now, where I'll display my whiteboard. So once again, the topic electromagnetic field. Let me share that again. So electromagnetic field it is. The concept in today's class is that we want to show some of the patterns of the magnetic field around the current carrying conductor. So I'm going to start from there. That very subtopic, patterns. Let me spell that right. Patterns of magnetic field. Around current carrying conductor. So let's discuss that concept first. A straight conductor carrying current can be shown to have, let me put that way, can be shown to have magnetic field around it. So the concept is that we allow a thick isolated copper wire to pass vertically through a hole in a cardboard sheet. We'll show something like that below. Then sprinkle some iron fillings uniformly on the cardboard. Around the vertical wire. So after you sprinkle some iron fillings uniformly on the cardboard around the vertical wire, then you now connect the ends of the wire to a battery and connect the ends of the wire to the battery. So once you've done this, you go ahead to switch on the current and place some compass needles around the wire. So this is like the explanation of how you go about, discovering the patterns of magnetic field around a current carrying conductor. So we are describing the process. So where I'm at now is I switch on the current and place some compass needles around the wire. And then the next process is to note the direction. Note the direction to which the compass needle points. Then we'll go ahead to switch on the current. Okay, yes. Switch on the current and note the swing. Of the needles, how they point. So I think we repeated something here. Okay. All right. So you see this last part looks as if we repeated something twice, but no, let me explain. I'm going to explain what happens in those two cases. So this is what we've written so far. I'm going to zoom in back. So patterns of a magnetic field around the current carrying conductor. A straight conductor carrying current can be shown to have magnetic field around it. Allow a thick isolated copper wire to pass vertically through a hole in a cardboard sheet and sprinkle some iron fillings uniformly on the cardboard around the vertical wire and connect the ends of the wire to a battery. This is two. Just keep this in mind. Come on. This is two. This is two. A battery. Then switch on the current and place some compass needles around the wire. Note the direction in which the compass needle points. Then switch on the current again and note the swing of the needles and how they point. So let me explain something in another paragraph. It will be observed that when current is switched on, and the cardboard is gently tapped, the fillings arrange themselves in a series of concentric circles about the wire as center. So that is the idea when you turn on the current to the first case. Then we also have as soon as the current is switched on, the needles will swing around and form a circle with the wire as center. So keep those statements in mind. The direction of the ion fillings depends on the direction of the flow of current. So let me give a diagrammatic expression to this. I'm going to draw a cardboard. Try that again. I assume that that's a cardboard. Then I'm gonna run through with a connection to the battery. I'm running through with a connection to a battery. So the ion filings. Now, let me indicate that electrons are flowing like this. They stand upward, sideways, like that. So this is the direction of electron flow. So like that. Then this guy is a cardboard. Then what we see is that the ion filings, they go around, you know, So this is what we see. So this is how it works. So these guys that we see here are the ion filings. Now, what did the note say? It said when the current is switched on, the needle will swing. So this is the direction in which the filings are moving now. Some moves like this, some moves like this. So let's start from the initial part. It said we observe that when current is switched on, the cardboard is gently tapped. The filings are arranged themselves in a series of concentric circles about the wire as the center. That's what we see in this area. That's what we see in this area. Concentric circles, the wire about the center. So keep that in mind. So we observe also that as soon as the current is switched on, the needle will swing around and form a circle with the wire at the center. So needle swings around, forms a circle as well, the wire at the center. The direction of the ion filings depends on the direction of the flow of current. So let's keep that in mind. But this is a diagram to express that concept. But please keep these points in mind. Yeah. So that's it. So switch on the current and place some compass needles around the wire. Note the direction in which the compass needle points. Okay, so okay. So let's move on to the next subtopic, which is magnetic field around a straight conductor carrying current. In this case, let me make some points. So the direction, magnetic field around a straight conductor carrying current. The direction and pattern of the magnetic field around a straight conductor carrying current can be determined using the following rules. So please focus. In this particular class, you are meant to read the notes and get the point. So get the essential points and take note of those things. They can be asked from you in your OBJ. Diagrams to just help you see some idea. But please take note of the point. So the following rules: A, Maxwell's corkscrew rule. And this states that, let me zoom in back. When a right-handed corkscrew is turned the direction of the motion of the cork represents direction of currents, while the direction of rotation of the cork represents the direction of the magnetic field. So it has given you something very solid there. Maxwell's cork rule. Please take note of it. You are meant to read this and get the main point. So it states that when a right-handed corkscrew is turned, the direction of the motion of the cork represents the direction of current. So motion of cork, direction of current. While rotation of cork, direction of magnetic field. So let me put this one in green. Rotation of cork represents direction of magnetic field. So keep that in mind. So then there is another one. Right hand grip rule. Some call it clenched fist. Some simply call this guy right hand rule. So the idea here is that you grip the wire with your right hand. So that your thumb points in the direction of flow of current. Your fingers point in the direction of magnetic field around the wire. So the idea here, I'm going to describe it in a diagram. So if I say this is the wire, for instance, or the conductor, and this is a hand. I'm trying to draw a hand. So I'm going to curve this part too much. Okay. So I managed to draw a manageable hand. Yeah. Hand is big, but then we'll manage it like that. Let me. So this is a hand, and you can see that this is the direction of the thumb. So, like we said, the thumb points in the direction of. So this is direction of the thumb, and that is definitely the direction of the flow of current. So if you hold a wire like that with your right hand, and you put your thumb like that, the current flows in that direction. Then, like this, just the way your other fingers are folded, that direction is, just the way that fingers point in direction of magnetic field, or we say the direction of the line of magnetic force. So the same thing as direction of magnetic field, the line of force. So we say fingers point in direction of magnetic field. So keep that in mind. This is the conductor or wire. So once you hold the wire like that, where your thumb point is the direction of current, and then the other fingers around that go around like that, they are pointing in the direction of magnetic field. So you have something that looks like this. This one is going like this, and there's one that is going around like that. So keep it in mind. So that is the right hand rule for a current carrying, for a straight conductor carrying, current. So having established this, let me go on to the next. Next subtopic. Yeah, let me go into the next subtopic. Okay, and that is force. Between two parallel current carrying conductors. So let me establish here that when two current carrying conductors or wires are placed parallel to each other, their magnetic field interact. Let's establish how they interact. When current flows in the same direction, the conductors will repel each other. And when current flows when current flows in opposite, for the first part, when current flows in opposite direction, the conductors will repel. When current flows in same direction, the conductors will attract. So let me give you a diagram to paint that idea. So we'll now go to the next subtopic. So if you have, in the first case, let's say you have a wire like this. Let me try and draw. So we have a wire here. And then we have another wire. So we have two wires like this, and let's say one is moving in the clockwise. This guy now, current is flowing through this guy in clockwise, like a clock. Let me make the direction red so that you see it. Clockwise direction. Let me do it like this. So current is moving in the clockwise direction. So, and then this other one, current is moving anti-clockwise. So once you place these two, let me put the line, let me put the line of force parallel to each other. So passing through the center. So when two current carrying wires are placed parallel to each other. So when we say parallel, kind of meaning that, okay, see the idea. So well, the force here is going to be the force of repulsion. This direction is opposite direction here in this case. So the force of repulsion. There's another diagram I'm going to draw. So this is what you have in the first case. So let me give you a couple of minutes to draw that. It's not a difficult diagram. So meanwhile, I'll be drawing the other one down here. Let me see. Force of repulsion up. And here we have one that appears like this. I want it to bend. There is a way. So, but when you have two of them flowing in the same direction, that is, some going like this, some going like this now, some going like this going like this, also this one going like this, some going like this, some going like this, some, so that they tend to, merge. So once they're going like that, and when we say it's going like this one, what it means, let me go back to the first one. What it means when it's going like this doesn't mean that something is going like this too. I mean, clockwise now when you're going like this. But this one opposite is going like this. So it also goes like this and keeps going. So but this one coming like this now, it's come like this and come like this. And keep going. That's how it works. So same thing. So the full idea is that it's moving. Two of them are moving clockwise. So this guy moving clockwise. In this first case, so it's clockwise, so it's anti-clockwise. But in this case now, both are clockwise. Since both are clockwise, kind of force between them the force of attraction. I'll keep that in mind. Yes. So let me go to the next subtopic. which is a force. So let me give you some minutes to complete the second diagram first. Not that hard, both are just moving in clockwise direction. Let's give you 2 minutes to complete that. Most importantly, this topic just catch the essential, little points. And as you are revising your notes, the textbook in these areas, just put down those important points. Keep reading, keep revising daily, keep asking questions. And yeah, ready for your exam that way. So let's see. First, next subtopic. First on a current carrying conductor in a magnetic field. So I'm gonna just make the notes here. A conductor carrying an electric current when placed in a magnetic field experiences a mechanical force. This can be demonstrated by using a setup shown below. I'm going to draw that later. Now using a setup shown below. Okay, let me draw that right now. So the idea, the setup, you are trying to place a current carrying conductor in a magnetic field. So the magnetic field, let's set it up first. We have two magnets, one here, one here. This is the South Pole. Let me put it inside South Pole, North Pole. And this is the South Pole, North Pole. Now we know that these two will, interact. They will North Pole and South Pole. So stuff will be happening right there. And if we remember really appropriately, things move from the North Pole and they successfully enter South Pole. So this is the direction of interaction happening here. So know that stuff is happening there. Then we'll now decide to place a conductor. This is the conductor. We'll place it, in that magnetic field. And place it in that magnetic field. So that's the conductor. Now, once you place it like that, let me now continue my note. Or let me first of all use the diagram to show you something with the left hand rule. So the left hand rule looks like this in this case. Sound very well. Now this sound is not on, you know. Okay. So the idea here is this guy is pointing like this. This one is not pointing. So you have something like this. Okay. Let me draw this better. This particular hand is kind of pointing. How would I do this now? Yeah, that's the direction where it's pointing. So that you don't get it. It's not pointing here. It's not slanting like this. This one is pointing like this one is pointing up. This other one is pointing something like sideways out towards you. It's pointing towards my face right now. Or like, yeah, something like this. So what we're having is something like this. Yeah. So that's the, yeah, that's what it is. This one is up. This one is X. Something like that. This one is, or let's say this one is, these two are perpendicular. You understand? These two are perpendicular. Like they have the angle of 90. This up too has the angle of 90 with the down. I mean everything down. So, but these two, just know that these two that you're seeing down, these two down are perpendicular. So that's how your finger is going to point. So if you try to do your left finger like that, do it in such a way that, these two particular hands are perpendicular. Then the other one pointing up is perpendicular to both of them. So that's how. So the idea here is now that if you put your hand like that, this up direction that we're seeing is the direction of the force. So this is what we call left hand rule. So the up direction is direction of the force. This particular one, this is up direction that I just talked about. That's direction of force. Then this side direction, right here, is direction of magnetic field. And this other last direction, let me give it a different color, maybe blue. That is direction of current. So I'm gonna see it up. Up, let me put the color again. Up you have red, down, up, you have red, that's force. Then this side, you have magnetic field. You will get to discover that the symbol for that is B, vector later in life. Then current, we see that down blue. We're just going to put I. So use black to write force, magnetic field. We abbreviate that. Then current. So that's just the idea. I need to give you a couple of minutes to draw and understand this left hand rule. So you see it. Told you perpendicular that is when you're putting the hand, you make sure that those two, there's an angle between them, 90. And then the one that is up is very obvious. So when you place it like that, that is the idea when you put when you put a conductor in a magnetic field, you get a mechanical force. And the direction of force is like upward. So This is the left-hand rule. I'm going to give you notes on that, but let me give you some more minutes to write down some things. So, and then we will go ahead to. So this left-hand rule, let me put in brackets. People call it Fleming's left-hand rule. Fleming's. So that's it. I believe that you've tried to draw. Now let me go straight into the next subheading. That is, oh no, not the subheading. Let me still continue explaining what I just drew up there. So because I said the last statement was this is demonstrated by using the setup shown below. Yeah, and I've shown you the setup. So in that setup, let me explain two metal rails fixed on each side of a powerful horseshoe magnet. So you see magnet there, horseshoe magnet. Are positioned, they are positioned such that a copper rod is placed across them. So when current is passed through, this copper rod, it is observed that the copper rod rolls along the rays toward the right. So by adjusting the rheostat, more current can be allowed. You know, rheostat is some form of resistor. So let's say I reduce the resistance now. You know that more current will flow. More current can be allowed to flow through the rod. So as current increases, your rod moves faster. So in this diagram, this guy is copper rod. So this is magnet. This is another magnet. Magnet. So rod moves faster. So we know that if the direction of flow direction of flow of current is reversed by reversing the connections at the battery terminal. The rod will be observed to move towards the left, opposite to the previous direction of motion. The idea here is just the point they are just making is okay. Right now, I discovered that after connecting the setup, I'm passing current through the rod. In the first case, the rod moves to the right. But they are not saying if I change the terminal of the battery, that is initially where I have, my positive, I put my negative there. I just change the direction, But where I have my negative, I put my positive. The idea is that the current direction will change too. And once you reverse the terminals like that. And so if you switch it like that, you also expect that the rod will now move to the left instead of the right where it was moving initially. So now we must also note that if you look at this diagram, you see that you place the rod across, right? You place it across the magnetic field. If, for instance, you place it parallel, if you don't place it across, if the magnet and the rod are parallel, this is a very important point. No force will exist. So we must have a perpendicular position for the two of them for force to flow. No force will exist through the rod, no matter the current. So if the magnetic field, magnet, you can put in bracket magnetic field, because it's the magnet that creates magnetic field. The magnet and the rod are parallel, no force will exist to the rod, no matter the amount of current passing through it. So a big idea there is that you must have the, the rod and the magnetic field perpendicular to each other in order for magnetic force to be created. So when we say electromagnetic field, you see that idea of the rod and current passing through it, that's an electric field, of course. Once you have current running through the rod, see this rod here, it's across this rod. Yeah, this rod in itself, as current is passing through it, creates an electric field. So the electric field must be perpendicular to the magnetic field for a mechanical force to be created. So that is the idea. So once they are parallel, nothing will happen. No force will exist. So no matter the current passing through. So let's now go ahead and, based on what we drew, we stated the Fleming's left-hand rule. Let's now state it right here. Fleming's left-hand rule states that if the thumb, so up here, let me go back up. That particular one facing up, the direction of the force, that thumb, of course. This guy is the thumb. So if the thumb, then the forefinger and middle finger. So I'm gonna say forefinger and middle finger. So let me quickly point at them. This is definitely the forefinger. And this guy right here is the middle finger. But see a lot is happening there. So if the thumb, the forefinger, and middle finger are held mutually at right angles, I explained this. The one facing up is at right angle. That's where I explained in this particular area, this portion. See it? That's where I explained the right angle concept. The one head up is at right angle to the two that are down. Then the two down are at right angle to each other. So this is it. The one head is at right angle to both of them that are down. And the two down, they are at right angle to each other. So I'll explain this. So if the thumb, forefinger, and middle finger are held mutually at right angle, to one another, with the forefinger pointing in the direction of the magnetic field, and that's what's happening up here. The forefinger direction of magnetic field. So the forefinger in direction of magnetic field. The second finger, the middle finger in direction of current. No, let's put it there. Yeah, middle finger in the direction of current. Then the thumb will point in the direction of motion. So, or you say the thumb will point in direction of motion or the direction of, let me not say direction of motion, but the thumb will point in the direction of the force producing motion. So that is the idea. So we have explained the Fleming's left-hand rule. We talked about the right-hand rule earlier on. Let's quickly make some points on the applications of electromagnetic field. I will say as a student, it is better you take notes, listen first. You might not get the full idea. Go and reread and make some points. I will tell you something very important in life at this junction. It is better to know, the little, be aware of some of these little things and know some of them than to not completely know them at all. Some of the ideas you have gotten in this class now will help you to get some OBJ questions. And if you are very serious, you are not supposed to fail anyone, then you will get also your theory questions in your exams. But let's say, something happens and you're not even, God forbid, you're not extremely serious. Just by you coming to class and then you reading on your own, which I expect you to do. And you have to be serious. It's not an option for you. You will know some of these points and then you'll be able to find. But if you are not aware at all, that's a different. You understand? So don't ever be tired of learning. It's better to be aware and read. You get the idea, then you're able to solve some problems than not to be aware at all. You are blank. You understand? So keep learning, keep pushing. Applications of electromagnetic field. Number one, electric motor. This is a device for converting electrical energy into mechanical energy. It consists of the following: a rectangular coil of insulated wire known as armature. So then see that's armature. AR, we write it in capital. RMATURE. So, and there's another part, a powerful magnetic field in which the armature turns is provided by two curved poles. Powerful magnetic field in which the armature turn is provided by two curved pole pieces. Okay, curved pole. Curved pole is like together. Curved pole pieces of magnet. So in this magnet, the poles are curved. Of not just ordinary magnet, powerful. magnets. Then the third one is made up of an accumulator made of split copper ring in two halves, which are insulated from each other. And the fourth part is you have two carbon brushes which are made to press lightly against either side of the split ring. So I'm going to correct something. Split ring commutator. So this thing is commutator. So this is a commutator. A commutator, not accumulator, commutator. So please adjust that. Not an accumulator. Please correct that. A commutator made of so the idea is that the two carbon brushes are now made to press lightly against either side of the split ring commutator. So those are the part of an electric motor, which is the first application of electromagnetic field. The second application is what I'll call moving coil galvanometer. Moving coil galvanometer. Moving coil galvanometer. So the moving coil galvanometer this galvanometer is one of the most sensitive and accurate methods for detecting or measuring extremely small current or potential differences. Sensitive and accurate methods for detecting or measuring extremely small current or potential differences. So the structure consists, or you say it consists essentially of number one, a light rectangular vertical coil pivoted such that it can move in a vertical plane Then we have two pads composed of two curved OPs of horseshoe magnet and a soft iron core or cylinder inserted between the poles. Then the third part is it is made up of two spiral non-magnetic control springs of phosphor bronze, each of which is attached to the jeweled bearing or spindle. So you must note that current enters or leaves the rectangular coil through this spiral springs. Now the last subheading before we call it a day in this class. In this subheading, I'll just establish a formula which we'll later use in solving problems, or which you can use in solving problems from your book, and I call it the force on a moving charge in a magnetic field. So it's more like the electromagnetic force. Force on a moving charge in a magnetic field. So we say it like this: the force F on a charge Q moving with a velocity V which must be less than the velocity of light. So the force F on a charge Q moving with a velocity V in a magnetic field. Like I told you that later you'll find out that magnetic field is given by this. In a magnetic field of strength B, the magnetic field strength is represented by B. B vector is given by force equal to charge times velocity times B. Take note of this guy. Normally put them in red. So charge times velocity times the B, which is the field strength. So magnetic field strength is B, velocity V, force F, charge Q. So this is the last subheading, and we will meet in our next class. Till then, keep studying, keep improving, keep learning. I'll see you again.